I would like to thank everyone that participating in today in FMRI webinar series. I think this is the last one for our webinar series. We have the privilege to have Dr. Li Zhao from Tsinghua University. And he's going to talk to us about interesting research that happened with the area that requires also the bike. Dr. Li Zhao is an associate professor and director of the Operations and Service Research Laboratory in the Department of Industrial Engineering at Tsinghua University, China. His research focuses on stochastic optimization methodologies and their application in supply chain risk management, logistics, and transportation operation as well. Of course, we don't forget the omni-channel retailing and logistics. His research has been funded by the Natural Science Foundation for China, very prestigious agency, and the Ministry of Science and Technology of China, as well as industry collaborators. He has served as the Secretary of INFOMS, TSL Society, and AA at the International Journal of Operation Society, and currently serves as Associate Editor for TS. I would like to mention that Tsinghua University, from my time I was a student, was one of the best universities in transportation logistics in China. And I am very happy to introduce Dr. Zhao. Dr. Zhao, the floor is yours. Thank you for the invitation. And also I would like to thank the IT FAU chapter that they put this webinar together. Dr. Zhao.
Yeah, thank you, Professor Kaiser, for this nice introduction. Okay, so shall I start now with my talk? Okay.
Yes, please.
So, yeah, thank you for the invitation to share our recent work on this free-floating bike sharing system. And specifically, we focus on the dynamic repositioning of bikes within a single cell. And I'm going to explain cell quick soon later. And this work was mostly by my PhD student, Xue Luo, and my collaborator at Tsinghua University, Professor Li Li, and also the Meituan, which is basically Meituan acquire one of the largest free-floating bike sharing system like Mobike in 2018. And Mr. Jianfeng Lin is in the unit within Meituan, which are in charge of the bike sharing system. So I think most of us, we know bike sharing system has been emerging as becoming more and more popular recently. And actually started very early in 1965 in Amsterdam, Netherlands. But maybe that was too early. That initiative turned out to be not so successful. And recently, bike sharing system, especially station-based, emerged and developed very quickly. But however, if we compare this bike sharing system station-based with free-floating, the free-floating bike sharing system grows even faster. So up to 2015, in the world, there were over 7,000 systems with 800,000 bikes. But ever since the start of the free-floating system, now we already have like 23 million bikes in 2018. And in a recent statistic, so both on the data of Mobike in Shanghai in August 2016, but in different scale, geographic scale. The first one, Li et al. 2020, So look at a small, like a downtown area, a smaller scale with only 100, like 100,000 trips, and they discover that majority of the back trips, back trip distances are within 2 kilometers, and most of them has a length of like a 1.2, 1.4. Basically, they have short trips. And the other study on a larger scale with 1 million trips in the same time period, but cover a larger area of metropolitan area of Shanghai. And of course, the travel distance becomes larger, like most of them within 3 kilometers, with the average travel distance like 1.8. But overall, we discover that most users ride bikes for short trips. And because of the large scale and also the travel pattern, so normally the company, they will decompose, like a partition their operating area into smaller scales, like they decompose them, we call it cells. So for example, in 2018, OFO, another bike sharing company, they divided the city of Nanjing into 288 cells. So it's shown in this graph. And so basically like Hello-Bike, Meituan, they all decompose their city area into smaller cells. And we also see that although we mentioned that 2 by 2 kilometer, but actually the shape and the size of the shell can vary depending on the demand density, distribution, trip patterns, and the geographic demographic characteristics. For example, if there is a major barrier like a freeway, a river, you do not have a one cell like cover that barrier. So you partition the cell alongside either side of the barrier. Okay, so and also I think most people when we talk about a bike sharing system, we understand the spatial and temporal imbalance. So spatial is like from A to B, like and from B to A may not be the flow, the demand may not be the same, and also this vary from time. So for example, in the morning, people tend to find a bike near the residential area, like outside the home, and ride the bicycle to a subway station. And at the end of the day, they want to starting from their office, ride to a subway station, and then from the subway station, find a bike, return to their home. So we see that this kind of a spatial temporal imbalance in the system. And to counterfight this imbalance, there are several different types of repositioning. The one is called the static repositioning. Normally during each night, the company, they will use some larger vehicle. While there are very few demand, they will use the vehicle to transport the bike to reallocate the bike into the city so that it can have the bike ready in the next morning. So we call it a static repositioning, mostly happen during the night. But however, during the day, as we show in the previous slide, in the morning, we may have bikes accumulated at the subway station from the residential area. And also on the other side, from the subway station, the bikes are leaving the subway station to the office area. And on the other hand, in the evening, we have the reverse movement. So we need to dynamically move the bike during the day to prepare for the morning peak, evening peak, such things like this. So this is a dynamic versus static repositioning. And also we have this notion of intra-cell and inter-cell, intra-cell repositioning and inter-cell redistribution. So normally, although the company, when they partition the cells, they try to contain the majority of bike trips within each cell, but they cannot avoid some kind of like escaping bikes. So for example, I find a bike within one cell, but then I took the right and I drop off the bike in another cell, because for the cells are only for the company for the ease of management. For customers, we do not have the notion of cell. We ride the bike based on our travel need. Okay, so basically there are intra-cell repositioning. We refer to one or more movers. They are assigned to this particular cell, and they are responsible to move the bikes within the cell. And for the normally this kind of movement is a smaller scale, and in China they use this electronic tricycle to make the movement. And on the other hand, if we have imbalance among different cells, and we may use a larger vehicle to do this inter-cell redistribution. And in this paper, we focus on within a single cell on the intra-cell repositioning. And these two type of intra-cell versus inter-cell, they also have a different scenario when they are used more frequently. So for example, if a company enter a new market or like a new city, a new operating area, so they may not have very good, very accurate demand forecast or estimation. So their initial allocation of bikes among the cells may not match the demand very well. So they need to frequently move the bikes among the cells. So the inter-cell redistribution is more frequently used in that stage. But when the market become more and more stabilized, the needs to move bikes among the cells becomes less frequently. They are mostly used for dealing with this escaping bikes. So intra-cell repositioning becomes to play a major role. But in any sense, even in the new market scenario and in the stabilized market scenario, it's always necessary to use both intra-cell repositioning and inter-cell redistribution. Just like which one is used play a major role. And these are the pictures we took when we started this work. And actually, the right one was me. And I just happened on my way to campus. I found this guy just drop off bikes in one of this location near my home. So I asked him to take a picture together with me. So we see like this mover move like 20, 30 bikes at the most among locations. Another feature of this free floating bike system is like the bikes are not only located at the stations, they can be dropped off anywhere as long as there's a legal parking space for bikes. The users have the freedom to drop off the bikes. And this is a map in Beijing, and you can see there are a cluster of bikes, and we refer to as gathering points. And there are also scattered bikes along the way when you travel between these gathering points. And so for this intra-cell repositioning scenario, the mover is responsible to reposition bikes among the gathering points. And of course, the gathering points are decided by the company based on the need. Where are the location the bikes tend to gather, accumulate, or at some time there are many clustered demand at these locations. And the mover also has the responsibility to collect the scattered bikes along the path. So when they travel between gathering points, they also collect the scattered bikes, move them to the gathering points. And the goal is to satisfy as many as possible demand at the gathering points. So the intention is not to satisfy the demand anywhere. Is they mostly are looking at the gathering points. So a brief literature review. So in fact, if you look at the literature on bike sharing system, you see many new publications almost every day. And we focus on the operational level repositioning, like every daily level. And also we look at the operator-based repositioning. And the other part, the other one is this user-based repositioning is like a city bike in the US. They gave this the bikers incentive to move the bikes to their desired location. But in our work, we look at the operator-based repositioning, which the bike sharing company move the bikes. And we look at the free-floating systems. And in short, our paper, we look at the dynamic intra-cell repositioning and with the stochastic demand. And we look at repositioning bikes among the gathering points and also collecting of bikes, scattered bikes on arcs. And we use the policy function approximation as our solution approach. And in brief introduction of the problem. So we look at a single cell and we represent the cell as a network with nodes and arcs. And the node set n represent the set of gathering points and 0 represent a depot. And actually in this setting, the depot is actually you can consider as an abstract setting. So sometimes it may be the starting point of the biker, of the mover, or it may be just like the mover enter this area. So the depot, we use the depot is only for the modeling as a modeling way for this vehicle routing type of models. It's just a location. And at the gathering points, we also have a capacity for how many bags can be gathered there. And the arcs, these arcs represent path. The mover may travel between the gathering points. So this is the arcs, and the arcs also have scattered bikes. We assume that the bikes randomly arrive and departure from the nodes or gathering points and also on arcs. And the mover has a capacity like it's shown in the picture, like an e-tricycle may have a capacity of like 20 or 30 vehicles. And the mover loads bike at every node. It loads back onto the vehicle or unload the bike from the vehicle to the nodes. So please pay attention that when we say load, we say load the bike onto the vehicle, not load the bike to the gathering points. Okay, and also along the arc, the mover only loads arc onto the vehicle. So the mover will not drop bikes anywhere along the arc. And the system dynamic is like during the day, like a working shift. The mover started with an empty vehicle. And at every time when the mover arrives at a node, we call it a decision epoch. The mover has 3 decisions. First, the mover needs to decide how many bikes I want to either load onto the vehicle or unload from the vehicle to the node, to the gathering points. And then the mover needs to decide what will be the next node to visit. So, and third decision specific to this free-floating bike sharing system is like the mover also need to plan like how many bags I'm going to load along on the arc when I travel to the next node. Here we put expected because sometimes you see there are like 10 bikes along the arcs, but when the mover travel along the arcs, there maybe user took some bike away. So here the mover can only have an expectation on the number of bikes to load. And the goal for the mover during the whole shift is to satisfy as many demand as possible at all the gather points. Okay, again, the mover do not intend to satisfy demand along the arcs. And we model this as a decision epoch. Like whenever the mover arrive at a node, this is a decision, we call it a decision epoch K. And this K, decision epoch K, the state we have the state variable include the current time, TK, and also the vehicle attribute, basically the current node, LK, and also the remaining capacity of the vehicle, QK. And also the mover knows the number of bikes at each node and also on each arc. And given the current technology, this is this is actually the reality. Even for us, when you open your app, you know the number of bikes around you. So this is also known to the system and to the mover. And again, the mover has three decisions: the inventory decision to decide on the loading and unloading amount of bikes onto the vehicle or from the vehicle. And this decision actually decide on the inventory of bikes at the current location. And the routing decision is to decide XD, the destination, the next node to visit. And this in route decision is like expected number of bikes to load on the vehicle. And when making these decisions, the mover also need to consider the remaining capacity of the bike, the vehicle, or the number of bikes on the vehicle, how many bikes I can unload from the vehicle, and the remaining capacity at the node and number of bikes at the node, and also the bikes currently scattered at the arc. So these are the decision. And the exogenous information basically is out of the mover's control. So this is just a random variable. We represent this delta D K on the node is the number of net back departures, meaning user took the bike away from the node. So this is delta D. When delta D is negative, meaning users are dropping off bikes at node I. And the other one is with IJ. So same thing is for the arc, the delta D. So we use the net departure to represent. So it can take either a positive or negative value. And the system transition is straightforward. The time is the mover starting from the current time TK and load the bikes at the current node and travel to the next node, and also the time spending on the arc to collect the bikes. And then this becomes the next time, arrival time of decision epoch TK plus 1. And also we maintain so the vehicle location becomes current when we decide on the next node to visit at K, and it will be the vehicle location of the K plus 1. And also we maintain the remaining capacity based on the unload vehicle and also the in route vehicle. And also we maintain the changes at each node and on each arc on the number of bikes. So the cost function is straightforward. We just want to record the satisfied demand between K and K plus 1. And at the time TK, we do not know about what happens between TK and TK plus 1. So we take the expectation. And the objective to maximize the expected total demand satisfied at the gathering points during the working time. So overall, we can summarize this in this diagram. So at decision epoch K, so we know all the state variable like time, location, remaining capacity, the number of bikes in the network, and we make the three type of decision: inventory decision, routing decision, in route decision. And based on this state decision, we observe the random arrival, and we can transit to the next state, and we can calculate the cost function, and eventually we maximize the expectation during the entire shift. And we want to find the best policy to do this. And so we follow this unified framework by Professor Warren at Princeton University. So basically, he classifies the methods in stochastic sequential decision making into 4 types of methodologies. So the cost function approximation, mostly they use a parameterized cost function at each period k and solve that at single period problem. And we use this policy function approximation. So basic idea is we design some policy and to find the policy parameters to decide on the decision given a state. And the value function approximation is like we approximate the value of being in some state and reduce, and then using the approximate Bellman's equation to do this. And the other one is the direct look ahead, is something like a rollout stochastic programming. And so, like we said, we use a policy function approximation. So we design policies at each decision epoch k. So for the inventory policy, so we use this natural 2-threshold policy, like a lower bound, upper bound. So at each decision epoch, so the equation is straightforward. So when we have a very few bikes, when the number of bikes is smaller than the lower bound, we unload bike from the vehicle to the node. And if we have more bikes than the upper limit, then we pick up the bike onto the vehicle. We load the bike from the node onto the vehicle. Of course, we need to consider the constraints of when we unload, we can only load the number of bikes on the vehicle. When we load the bike onto the vehicle, we need to know we can only load up to the remaining capacity. Okay, so this is the inventory decision. And how to decide, we cannot have many L for each T and for each I, many U for each T and for each I. There are going to be too many parameters to tune. So basically, we define 5 parameters. So the plus sign is for the supply node, meaning we have more bike arrivals than bike departures. And the negative parameter is so the minus parameter is for the demand nodes. Okay, and okay. So and this tau L is for the looking ahead time, because we do not want to be myopic. When we look at demand supply, we also want to look ahead this amount of time. Sorry that I was distracted a little bit because of my cat. I shut my cat out of this room, and he was screaming out of the room, and he was happy. Yeah. So okay. So I was distracted a little bit. Sorry about that. Okay. So once we decide on the supply node or demand or balance node, so we use two sets of parameter. So when the node is a supply or balance node, we use theta plus the underscore overscore as the parameter. When it is a demand node, we use this minus theta as the parameter. And you see that we use this tau L to look ahead tau L times for the estimation. And the alpha is depending on whether the arrival rate, the difference between arrival and departure is large or small. So if we look at the lower one, meaning if it's a demand node, and if the demand is larger, meaning the departure rate is larger, then we need to increase the upper bound. Okay, and once we decided the number of bikes to load onto the vehicle or drop off at the node, the next decision is which node I travel to the next. And then it depends on how many bikes on the current vehicle. And intuitively, if you have many bikes on the vehicle, then you are looking at which node need a bike. So you look at the demand node. And on the other hand, if you have a very large remaining capacity, meaning you have very few bikes on your vehicle, then you need to look at where are the nodes. There are more bikes than needed, so you need to go there and then load back onto the vehicle. And we use this. So the basic idea is you look at the expected, the anticipated unmet demand. When you have many bikes on the vehicle, you look at calculate the anticipated unmet demand of all the nodes, all other nodes, and you find the most needed one. And but if we go to most needed one, it may be very far away. So we take a ratio beta. So for whatever the needed the demand node with more demand than this beta of this largest demand, we include all of them and we pick the shortest, the one with the shortest travel time. And we do the same for the other part. The only thing is we look at where we want to pick up bikes. And the time when we do the anticipated unmet demand or anticipated loading amount are different. So the anticipated unmet demand is for every node. We look at if we arrive at that node, sorry, after we arrive at that node, we look at tau d times. So the idea is if we do not visit that node, then this unmet demand is large or not. Okay, which one, because you cannot satisfy the demand before you arrive at. When you arrive at the node, the next node, then you unload the vehicle to satisfy demand from then on. So this is the time period we look at. And when you look at this anticipated loading amount, the time period is this one because you only load time along the arc, and also you can only load the bikes when you arrive at the node. So whatever bikes arrive at the node later on that, you cannot load. So we look at this period of time. Okay. And the other decision is this en route. So the en route decision is like we also put a time limit on the loading time, arc loading time. So this is tau LK and XDKD. Basically, this is the travel. So this is the travel time, travel distance between current node and the next node. And tau A is sorry, this tau sorry. Tau LK is the travel time, and tau A is this arc loading time. And we take a parameter to put a limit because we don't want the mover to spend an infinite number of time, only collect as many bikes as possible on the route. They need to satisfy the demand at the gathering points. So this is the meaning of this time limit. Okay, so basically we have this set of like 9 parameters. So although there's 9, we need a lot of data to train these 9 parameters. So we use this method called optimal computing budget allocation. So the idea is if you have a fixed computing budget, how do you allocate your computing effort to have a good estimate and select the best parameter set. So the basic idea is you do not want to spend too much time on the hopeless or not the point like the parameter setting not likely to become a good setting. Okay, and also the evaluation of each parameter configuration, the parameter setting is expensive because we need to simulate. Under this set of a parameter setting, we need to run simulator with multiple days. Okay, so this is the pseudocode of this OCBA. So the basic idea is for every parameter setting, there is an initial simulation replication, and after that we have a current best solution as B, and then we also know the sample standard deviation, and then we allocate the the next round of the budget using this set of equation. And the idea is the larger the variance, because you are not sure whether it can be low or long because the variance is large. You do not have very accurate estimation. The larger the variance, you tend to spend more simulation to have a more accurate estimation. And the smaller the distance between that I to the best value, because it's so close to the best one, you want to know which one is actually better. So you tend to spend more effort there. Okay, so we use the data from Mobike, currently Meituan, in an area in Beijing. This is roughly 2 by 2 kilometer, and we identify the gathering points. They are like a shopping mall, office building, like a subway station, something like so. Basically, an apartment building. So these are the gathering points defined by the company, and also we can see that in the data. And we look at the afternoon shift from 3 p.m. to 8 p.m. And this time actually cover before the evening peak, during the evening peak, and the post evening peak. And we discretize the time into 5 minutes. So every 5 minutes we call it a period. Okay, and the time interval is like because we need to model the bike arrival and departure, so we call it supply rate or demand rate, estimate from the data. So we decompose the time into 1 hour each, 5 time intervals. So time interval is how we estimate the data, and within each interval we assume the arrival departure rate or supply demand rate is stationary with independent Poisson process, and we estimate these lambdas also from the data. And this will show from 3 to 4, 4 to 5, 5 to 7. So each of these represent one time interval, and we see that the node 1 to 7, we call it an evening peak demand node, because during the evening peak, like they need more bikes because there are many users. For example, they leave their office, they want to ride bikes to a subway station. And nodes 8 to 10, we call it evening peak supply node, because they have more and more bikes accumulated. They supply bikes. And these are somehow the details we allocate. So from the data, we allocate the bike, we estimate the arrival rate of the bike on the node, and we use the proportion to allocate a bike between nodes and arcs. Then we can back calculate the arrival rate to the arcs. And once we decided the overall rate to the arc and to the node, we set the arc arrival, individual arc arrival rate at proportional to the two ends. So arc ij lambda is proportional to the lambda at node I and the lambda at node j. We take the proportional to that setting. Okay. And for the travel time, it's 24 kilometers per hour. And the initial allocation, we allocate half and half, half at the nodes and half along on the arcs. And initially we have 300 vehicles within this cell. And we benchmark with the two policy. One is this non-repositioning policy, which is actually this is not a real policy. Basically, it's do nothing. This one we just use that to evaluate the value of repositioning. So it's like for whatever policy we compare with do nothing. And another one, sorry, one benchmark we compare with is from the literature, and they also based on the current shortage and the supplies to make the inventory decision, and then but however they do not look forward into the future. So this is a plot like for the STR policy. So they use this lambda parameter to decide. So basically, if the number of bytes is smaller than lambda, this gamma qi, then I drop off bytes. If it's larger than 1 minus gamma qi, then we take bytes away. And so this is the basic for inventory decision. And for the routing and for the in-out decision, we make it similar to ours. But the difference is they do not anticipate the future. They only look at find the imbalance, the most imbalance, the nearest one, sorry, the imbalanced node, and pick the nearest one. And another one is the mover's practice. So basically, the mover they tend to look around and using a greedy way. They just when the mover has the bike on the vehicle, and they will look at which one need the most, then it will travel there, but without anticipation into the future. And for each policy evaluation, we use 200. Basically, we replicate 200 days or 200 shifts, and we spend like 24 hours to train the OR parameter, and because there are only two parameters for the benchmarking STR policy, so we spend 4 hours to find that parameter size. But once the parameter is decided, to decide on the decisions is only take like a centiseconds to make the decision. Is a real-time decision. And we see that looking at the demand satisfaction ratio, compare with the do nothing, all the policy basically you can improve the satisfaction ratio, and of course our policy function approximation perform the best. And we also look into the behavior, how it perform better. So first we look at evening peak, like during the afternoon, between 3 to 5. We see that the dark bar, which represent the PFA or policy, is actually there are some. So the vertical axis is satisfied demand. We see that at node 8, 9, 10, those are evening peak supply node. We satisfy less demand than other policy, meaning we have a more demand loss than other policy at these nodes. Note that the vertical axis, the max is 30. But however, when we look at between 5 to 7 during the evening peak, then we satisfy the dark bar, satisfy many more bikes at the demand node. And note that this maximum value is 90. So basically so the basic idea is that we sacrifice very few demand at the supply node, and we satisfy more during the evening peak hour at the demand node. Okay, and even at the post-evening peak, we still satisfy more demand. And this is the satisfied demand, and during the evening peak and the post-evening peak at the supply node. So the vertical axis this is a satisfied demand. And then on the next page, we look at the behavior. This is the loading amount. So positive value is the loading amount of number of bikes on the vehicle. So we see that before the evening peak, during the afternoon, basically the idle time, the balance time, the mover load many bikes from the demand node, and they unload the bikes, load from the supply node and unload at the demand node. So this is the pre-evening peak behavior. And I replay the previous slide. So that results in the less satisfied demand during the pre-evening intervals at the supply node, because we move bikes away from them. But then we satisfy more demand during and after the evening peak. And now we look at the loading amount. During the evening peak, we see that we basically unload still every policy load a bike from the supply node and unload the bike at the demand node. But still this dark policy, they do much better. But for other policy like this STR, they started to load many more bikes from the supply node and unload at the demand node, but it's kind of like too late. And we also observe that our loading unloading behavior has the largest, the best correlation with the supply, the net supply and demand. Okay, so basically our moving behavior is consistent with the supply and demand pattern. And this is from the time view. So we look at the two nodes. So this plus node 8 represent a evening peak supply node, and node 5 half. And then we look at what if we have more and more bikes on the arc, what may happen? So we increase this percentage to 100%. So we see that when more bikes are scattered on the arc, all the policy behave worse because there are fewer bikes on the gathering points to satisfy demand, but PFA performs the best. But when this when 0%, meaning all the bikes are at this gathering points, because we have plenty of bikes, relatively sufficient bikes to satisfy the demand. So PFA, so the even compared with them to nothing, all this policy, the gap is smaller. But when we have more and more bikes on the arcs, so the gaps is larger. And also we look at the total loading amount at the demand, evening peak demand node, supply node, and on arc. We see that the dark bar, we put more bikes onto the demand node so in every scenario. Okay. But when there are many more bikes on the arc, so basically there's a limitation you can put because there's a bike capacity, the vehicle capacity constraints. And also we see that when the percentage of bikes on the arcs are very large, like 70% of them or 100% on arcs, the PFA policy already started to pick up more bikes, collect more bikes along the arcs. Okay, and this is the total number of bikes. So basically, sorry, let me go back one. So this is the total amount of bike amount, like a loading and unloading amount. And this slide is to say at 5 p.m. So basically, during the afternoon, we prepare for that. And at 5 p.m., at the beginning of the evening peak hours, we see that the PFA has more bikes ready at the demand node than other policy. Okay, just to summarize our work. So we study this dynamic intra-cell repositioning of bikes among the gathering points. At the same time, we consider the collection of bikes scattered along the arcs. And we consider stochastic demand both at the gathering points and also along the path. And we model this as a Markov decision process and using the policy function approximation and using the optimal computing budget allocation to train the parameter. And we study, we show using the real data, we show that the PFA outperform the benchmark policies. And we also show the value of repositioning and the behavior of repositioning and the impact of a bike scatteredness. And these are some of the reference. Yeah, thank you. This is the end of my talk.
Thank you very much, Dr. Zhao, for this very interesting presentation. Are there any questions for Dr. Zhao? You can either type them in the chat or you can unmute yourself. I don't see any questions in the chat.
I have a question.
Yeah.
Vasya?
Yes.
Hi, Dr. Zhao. It's very interesting presentation. So it's like dynamic positioning problems. So as you mentioned, you use the data from Meituan. Have you ever talked to the person from Meituan that if they use the similar like algorithms or the policy, the method to repositioning the bikes?
Okay.
I'm just wondering, yeah.
Yes, this is actually a very good question. In fact, let me check my calendar. Actually, I gave a talk at this Meituan, the biking. Basically, this biking, not only this bicycle and also e-bicycle. So I gave this talk in that team. And also one collaborator, Jianfeng, he's the AI, so basically he's the algorithm team, the leader of the algorithm of that unit. So this is the first question. Yes, I did communicate this work with Meituan. And the other one is our policy, like we say this myopic policy, the status quo is mostly mimic their current practice.
Thank you so much.
Yeah.
Thank you.
Thank you, Dr. Zhao. Any other questions? Okay, I don't see any other questions. Maybe we can end this. Yeah.
Yeah, just one. So basically, I can share with you the file of this presentation later on.
Mm-hmm.
And also, this paper just recently was accepted at transportation science. So, but it only went to production like yesterday. So I'm not sure when it will be publicly available, like online. So if you're interested, I can send you the manuscript. Not the final one. I mean, not the online one, the official one. I'm happy to share.
Yes, of course. And then if they approve your work, we can post it also on our website, this presentation as well with the recording, if that's okay with you.
Okay, sure.
Okay, thank you very much, Dr. Zhao, for this very interesting presentation. I would like here to mention that our next event will be hybrid on January 26 with Dr. Dimitriou, and you're going to receive more information for this event soon. I wish you all happy holidays, and Dr. Zhao, thank you again for presenting today.
Okay, thank you for the invitation. Yeah.